In this video, we're going to take a look at how we represent functions. First, we need to talk about the different categories of functions, and there are two distinct types or distinct categories of functions in mathematics. We have algebraic functions that work according to the algebraic rules, and basically they use arithmetic to describe themselves. So they can be defined using the four basic operations: addition, subtraction, multiplication, and division. So those are our rational functions and our polynomials. Then we have functions called transcendental functions. They transcend arithmetic and they give us these unique types of functions that act outside of those for arithmetic operations. So things like trigonometric functions, exponential functions, logarithmic functions, and there's some other screwy ones, like inverse trig functions and so on. But these are called transcendental functions. One of the ways that we describe or display or represent functions is through a graph, and we oftentimes will use a graph to represent a function. So we have two different examples here. We have a snapshot of a traveling wave packet, whether that's a little packet of energy or light, whatever it may be, and a probability curve here of getting at least one double six after n number of throws of two dice. And so we can represent these two functions, these two ideas, with a graph, and it gives us a physical representation. An important thing to note about graphs is we can do these analytically, or we can use technology to describe or to actually generate the graph for us. And it's important to note that it is essential to be able to integrate both of these to have success in calculus. You need to be able to graph things analytically and do them in your head, so to speak, but you also need to be able to use technology to generate a graph for you. The most basic type of function that we'll represent is a line. And so this is an example of a linear function. And to have a linear function, what do you need? You need 2 points. If you define 2 points, then you can create a line. And we know we can do that by getting the slope. The slope is the rise over the run. We can calculate that, and then we can use one of our many equations of a line to solve for any other unknowns. Basic Algebra 1 stuff. We can also break lines into segments and get what we have here in what we call a piecewise function, where we have segmented our domain from x less than 2 and x equal to 2 and x greater than 2. Our range is different for each of those sections of the domain, and it's defined by a different function rule. An example of a piecewise function is listed here, where this looks like it's just going to be a rational equation, but upon further examination we see that, well, hey, this is just a line with a hole in it, because this top has the factor of x minus 2 in it, because x squared minus 5x plus 6 is really x minus 2 times x minus 3. Now, if you're not able to see that right off of the bat, that's something that you're going to need to practice in order to be able to have success here in calculus. You need to be able to see, hey, this is going to be a line with a hole. And why is there a hole? Well, we can't have the domain of 2 because that gives us a 0 in the denominator. And so that's a line with a hole, and that's a part of this piecewise function where we're defined by that function, that rational function, for everything but x equal to 2. And at x equal to 2, we're equal to 1. And so we just have this point right here. Another type of function that we could have that's similar to a line is an absolute value function. And this is y equals the absolute value of x. Now, you should have in algebra defined this using a piecewise function to say that, well, this is really just 2 line segments, right? This is going to be y equals x when x is greater than 0, and it's going to equal negative x when x is less than 0. And so then you might ask, well, what about when x is equal to 0? Well, we can just make one of these two constraints equal to, and it gives us this absolute value. Now, this idea right here is very important. You need to be able to take an absolute value function and split it into a piecewise. And so that skill right there, that ability, is going to be something you're going to need to have in your back pocket as we move forward. As we move up through the higher order polynomials, we have linear functions, that's x to the power of 1. Then we have quadratic functions where we have x to the power of 2. We have quartic functions where we have x to the power of 4. And then we have polynomials to the power of 6 where we just have x to the 6th. And this can keep going on and on and on. Now, something to notice here, these are all even powers depicted here. And notice they are all even functions. They're all symmetrical about the y-axis. And that is no coincidence. All origin-centered even polynomials will be symmetrical about the y-axis. Conversely, all odd origin-centered polynomials will be symmetrical about the origin, which makes them odd functions. And so we can see as these powers increase, it changes the shape. The overall general shape, they are similar, but we change things slightly depending on the power. All of these graphs, when you see an x to the 7th, an x to the 6th, an x to the 3rd, you should have a general idea of what that looks like. I'm not saying that you should be able to graph it perfectly, but just knowing the general shape of an x to the 5th is going to be important. You need to know that it's going to give us this S shape, and depending on what the terms are outside, we can then get a higher peak and then a lower peak before it continues up. When we have rational exponents, like x to the 1/2 or x to the 1/4, x to the 1/6. Now remember, what is this? This is the square root of x. This is the 4th root of x, and this is the 6th root of x here. And so looking at the general shape of these, they have kind of the same shape, except we see the little difference in how the severity of their growth at the beginning and how they actually intersect with each other, and the radical x climbed more quickly in the end. Once again, these are just little things, general ideas that you should know, general pictures that you should have of these functions. Last slide was all even roots, odd roots. Look similar, except we have this left part. Now, why didn't we have that left part with the even roots? Well, that's a negative inside of an even root, and we know that that gives us a non-real result. So that constricts our domain. Notice with the odd roots, our domain is all reals. Even roots, our domain is limited to positive numbers. And 0, so really it's just non-negative numbers. Rational functions are a little more tricky in that we can get these asymptotes, and we get asymptotic behavior. Now, one of the things to keep in mind, vertical asymptotes, like we have here at x equals 1, you cannot cross. The function cannot cross those because our domain is not defined there. However, horizontal asymptotes, such as y equals 3 here, those can be crossed. A lot of times it's a common misconception to think that, oh, you can't cross any asymptotes. No, that's incorrect. You cannot cross vertical asymptotes. However, you can cross horizontal asymptotes, because horizontal asymptotes do not describe the entire function. They describe the end behavior of the function, meaning what is going to happen at the extremes. At very high x's or at very low x's, what does the function do? It approaches that horizontal line. So this function does cross the horizontal asymptote there and there, which is okay. It just then approaches, it's going to level off. As we go this way, we're going to approach y equals 3 from the negative end because we're below it. And over here, as we go to the left, we're going to approach y equals 3 from the positive end. And so we say the asymptote y equals 3 is a horizontal asymptote. Now, where does this come from? And this is something that may be a little rusty for you, but you should be able to identify this based on just the function. Looking at this function here, you should be able to identify, okay, I have cubic over cubic, so that means that I'm going to have the same growth rate on the top as I do on the bottom. So as x's get really, really big, this is just going to settle at the ratio of the coefficients. Well, that's a ratio of 3 to 1, so y equals 3 is the horizontal asymptote. Where do the vertical asymptotes come from? Well, that's when we get a 0 in the bottom. So you set the bottom equal to 0 and solve. Now, if you cannot solve that cubic, there are some techniques that we can go through by factoring or by using some special formulas, but in this case, we actually have a pretty nasty function in that we get an irrational number where our root is, just a little under 1, and so we can find that through graphing or using some type of calculator or something like that to give us that answer. But the key is you need to understand, where does the vertical asymptote come from? It comes from when the denominator is equal to 0. Another way that we can represent functions is through a table. And one of the things that a table does is that it lays out the data points for us. And so if this is real life data that we're collecting, we know what is the actual data, and then we can maybe make some inferences from that data. But we can't necessarily get a good picture of the function because all we see are data points. Graphs give us a nice physical representation that we can interpret. However, data points, if this is something that we're collecting, this gives us the true story, and then we can try to make inferences from that, whether we plot it and try to fit a curve to it, whatever it may be. So by plotting those data points, we can see that, hey, we look like we're curving up and to the right here, or at least, if nothing else, it's increasing. It's an increasing relationship. We see that we have a relationship. Maybe it's linear in this portion. Maybe it's quadratic through the whole thing. We can dig a little deeper to tell, but we see that positive correlation and that positive relationship. And we can either use traditional analytical techniques or technology to actually fit a curve to those data points. So let's say we have this function f here, and I want to define a new function g to say that g is the slope function of f, meaning that g is going to be defined as the slope of the pictured graph f here for any given domain. And so in order to come up with that graph, we need to identify, all right, well, what's happening to the slope in f? Well, first off, from -1 to 1, we know that we have a linear relationship, so the slope is constant. From 1 to 2, we also have another linear relationship that's different, but it's constant in that period there. And then from 2 to 5, we have another linear section, which is going to give us a constant slope. Another thing we can point out, this is positive over here, this is 0, this is negative. So we know that this g function, whatever it may be, is going to have a positive constant value, a 0 value, and then a negative constant value based upon the slope. How do we calculate that slope? Use our Algebra 1 techniques, count the rise over the run, and we can find those. And so this piecewise function is g, which is the slope function of the pictured f. We could have the same idea to say that, okay, we have this function f here, new function f, and we're going to define g as the area under this function, the area under the curve. And so a of 2, or if we want to call our area function a here, a of 2 is going to mean this area right here. And a of 5 is going to mean this area right here. And so we can calculate those individually or to come up with points, or we can try to come up with a function that represents that. So if we look at these as, say, well, instead of having a hard fast 2 or a hard fast 5, let's just call this x. And as x moves this way, what's happening to our area function? Is the area increasing? Is it decreasing? Is it staying the same? And so we see that, well, the area is obviously getting bigger, so we need to have an increasing function. But there's a major change here that happens at this x equals 3. And so our area function is then going to be split up into a piecewise function. Using a little bit of geometry and algebra, we see that from 0 to 3, the area function acts as x squared, and from 3 beyond the area function acts as 6x minus 9. Now, this technique here, this actually is a huge foundation of about half of the calculus course, and it's something that we'll get into in the second half of the course, whereas that slope function is primarily the first half of the course. Now, obviously, we're going to dig into those ideas a little deeper. These are just kind of scratching the surface of the iceberg here, but these are the two foundational building blocks of calculus. The last thing I want to talk about in this video is transformations of functions and how we can move these functions up, down, left, right, stretch, compress, and change them both vertically and horizontally. So first, if we look at this black curve here, and we call that f, we can shift that up or down depending on what we add on the outside of the function. So if we just add 3 on the outside, that shifts the whole thing up 3 units. If we subtract 2, we're shifting the whole thing down 2 units. Okay, pretty intuitive. Add 3, go up 3, subtract 2, go down 2. Now, what's not as intuitive, if we were to add 3 on the inside of the function, so add 3 to the domain of the function, not to the range, that's actually going to shift it to the left 3. If we're going to subtract 2 on the inside, then that's going to shift us to the right 2. A little counterintuitive in that subtracting goes to the right, adding goes to the left. Now, if we multiply the function by some factor or some constant, then this is going to either stretch or compress. If we multiply by a number greater than 1, it's going to stretch it. If we multiply it by a factor that is less than 1, then, and we're talking less than 1 being between 0 and 1, the absolute value is less than 1, then we are going to compress this and kind of squish the function down. Along with that, if we throw a negative in it, that will flip it vertically. So multiplying by a negative, we actually flip the function itself, the graph of the function, vertically. If we were to multiply on the inside of the function, now with certain functions like the parabola pictured here, it kind of looks like the exact same thing that we just did. However, it is a little different in that multiplying inside the function, we're actually stretching or compressing horizontally. With parabolas, it looks very similar. It's just the factors are off by a little. By putting a 2 inside of being squared, you're actually multiplying by a factor of 4 on the outside. But anyway, this is similar to the stretch and compression vertically. However, things are, once again, a little counterintuitive when we deal with the horizontal. If we're multiplying by a number that's between 0 and 1, that's going to stretch it or broaden it horizontally, whereas if we're multiplying by a number that is greater than 1, then that's going to compress it horizontally, which appears in some functions to look like a vertical stretch. If we throw a negative into this mix, that is going to flip this thing horizontally. So this portion that was going up and to the right in the black curve, now in the blue curve is going up and to the left, and the portion that was going down and to the right is now going down, or excuse me, the one that was going down and to the left is now going down and to the right. And so we get that horizontal flip. So this example here shows that we have the black curve y equals x squared, and we have 3 other translations of that. Now you should be able to look at this and be able to tell me what is the function of a, b, and c based off of the fact that it's just a translation of the parabola y equals x squared. If you cannot do that, then you will need to do some extra practice to get to that point where you can figure out, okay, this is shifted to the right 2 units. How do we accomplish that in the y equals x squared? You know, the green one is shifted down and it's also stretched horizontally or compressed vertically. Which one is it? How do you figure it out? Parabolas are not the only functions that can be stretched or compressed. Any function can be. Here we have an example of stretching and compressing the basic curve of y equals the absolute value of x. This final slide here summarizes all of our transformations from the factor of c, a, and b and what those do to our function and its graph.